Welcome to a tutorial on the 8085 interrupt based instructions. Okay, so whenever you're gonna work with interrupt related programs, you need to use this kind of instructions as I'm going to illustrate right over here. Okay, so let's just divide the page into columns. Alright, so you start with the enable interrupt instructions, or the EI. Okay, so what this particular instruction does, it sets the interrupt enable flip-flop on the 8085, and thereby with this process it just enables all kinds of interrupts that are there on the 8085 microprocessor. Okay, so as you can see, this particular instruction, but it doesn't have any kind of operand as such, but its main job is to set the interrupt enable flip-flop and correspondingly enabling all kinds of interrupting facilities that are there on the 8085 microprocessor. So whenever you're using this kind of, whenever you're working with a program that involves interrupts and all, and you want to enable them, then you just go for it straight and just write there EI, okay, in your program. So whenever the 8085 would just encounter this particular instruction, EI, okay, it'll automatically enable all the kinds of interrupting facilities that are there present in it. Okay, so with the use of this particular instruction EI, okay, the flags remain unaffected, and this instruction is just a single byte instruction. Okay, so next we move on to instruction number 2, that is the DI instruction, or which actually means the disable interrupt. Okay, and it just performs in the opposite way, the exact opposite way in which the EI instruction actually works. Okay, so it basically, well, what it does is that it just resets the interrupt enable flip-flop on the 8085, okay, and thereby in doing so it just, well, disables all the interrupt facilities. Okay, and this DI instruction is also a single byte instruction like that of the EI, okay, and also the flags, they remain unaffected, okay, under the use of this particular DI instruction over here. Okay, so apart from that, so whenever you need to disable the interrupting facilities, you just declare this instruction straight away like this, DI. Okay, so whenever your 8085 microprocessor would just find it in the program code, okay, it'll automatically just disable the interrupts. Okay, now one thing I'd like to add over here, well, all the interrupts, okay, starting from the INTR, RST 7.5, 6.5 and 5.5, they can be, well, enabled or disabled depending upon the programmer. But here the trap interrupt, okay, the interrupt named trap, okay, which is the most important of them all, it can't be controlled with these instructions. So in all the descriptions, it's better to write except trap, because the trap is not, well, enabled or disabled with these instructions. The trap remains enabled all the time. So whenever an interrupt would fall, interrupt signal would just fall on the trap pin of the 8085, it'll automatically receive it, or rather take it as an interrupt request, okay, and start executing the program it would just, well, do the needful correspondingly if the program is designed to do something like that. Okay, so that was how you can, well, enable or disable the interrupts. And also it should be kept in mind that if, let's say, we were executing an interrupt based program on the 8085 and suddenly, well, there was a system reset, okay, if there is a system reset, okay, something like that, or if currently the 8085 has already taken or recognized an interrupt request, then automatically the EI instruction needs to be re-declared, okay, in order to re-enable the interrupting process. So whenever these things happen, okay, whenever there's a system reset or an interrupt is acknowledged by the 8085, all the other kinds of interrupts over there that are present on it, that are, well, controllable except the trap, they remain disabled as long as the interrupt request is being executed. Okay, so that just happens automatically. And you might, well, then ask a question, then why do we have the DI instruction then? Okay, let me just tell you, the DI instruction is used only in the cases of emergency. So whenever there is some sort of a code or some part of the program that cannot be interrupted under any circumstances, over there we can just use the DI instruction for the security, or just in order to manually disable the interrupts using program code. Okay, so that's how these instructions basically work. And then we just move on to the instruction number 3, which is basically a category and includes 2 instructions, the sim and the rim instructions. Okay, now these are known as the maskable interrupt instructions, and they are just valid for the RST 7.5, 6.5 and 5.5 interrupt lines. Okay, and like the previous examples, the previous instructions, they don't have any kind of operands. Okay, now let's just start with the sim instructions first. Okay, now the sim instruction is basically what known as the set interrupt mask. That's what the abbreviation or the instruction basically stands for. Now this diagram, as you can see on the right, can be used to describe how the sim instruction works. So you see, basically what happens is that that's the yellow box, okay, corresponding to the 8 bits of the D, starting from D0 to D7. Okay, so these 8 bits are actually the content of the accumulator register. So these actually is the 8-bit content, okay, of the register A. Okay, that's the accumulator. Alright, so you can see here that whenever we're working with the sim instruction, if the accumulator data byte is such, we can then basically each of these bit positions in the accumulator data, that has a special meaning. Okay, and these are actually these are specifically applicable for that of the RST 7.5, 6.5 and 5.5 interrupt lines. Okay, so here you can see the bits D0 to D2. Okay, they represent each of these RST lines, starting from where D2 corresponds to 7.5, 1 to 6.5 and D0 to 5.5, okay, interrupts basically. And as I told you all that these interrupts can be masked or can be left unmasked, okay, or available. So this means that we can either disable the interrupts or enable them at our will. That's just totally dependent upon the programmer's wish. Okay, so if we put the bits D0 through to D0 through to D2 to all of them, we can just, if we just keep them 0, okay, then each of the interrupt lines 7.5, 6.5 and 5.5 respectively would remain available for receiving any kind of interrupt request. Okay, so those lines will be just active. Otherwise, if we just keep them at 1, okay, at a logic 1 value, the D0 through to D2 bits, then the corresponding interrupt lines, okay, the RST interrupt lines would be masked or disabled. Okay, now in order to basically enabling in order to keep this facility of enabling and disabling each of the interrupt lines, okay, there is another control, that is the bit D3, okay, which is known as the mask set enable, or MSE in short. Okay, if we keep a logic 0 at the bit D3 positions, then bit D2 to D0 will all be ignored, okay, remaining that meaning that these bits would just not be taken into account, or they will just regard it as that all these bits are just disabled. It will be regarded as something like that. Okay, and if we keep the MSC bit, that is bit D3, at logic 1 level, then the bits D2 to D0 would just be masked. I'm sorry, ignored over here actually means that the corresponding RST lines, okay, I just made a mistake over here, okay, just don't mind about that. Okay, so if we keep the mask set enabled, it's the MSC bit, that's D3 to logic 0, then this means that the RST 7.5, 6.5 and 5.5 lines are unmasked. Okay, so they'll just not be masked over there, and the masking of those bits would just, of those lines would be ignored. Okay, and on the other hand, if we just keep the MSC bit, that's bit D3 to logic 1 level, then the bits D0 to D2 corresponding to each of the RST interrupt lines would remain, or rather would be masked. Okay, so you can just use this control to mask all of them. Alright, next comes the bit D4, that is the R7.5. So this is an additional control on the RST 7.5 interrupt line, where if we'd keep the D4th bit to logic 1 level, okay, then the flip-flop, the input flip-flop present at the input of the RST 7.5 interrupt line would be reset. So that particular input flip-flop would just be reset if the bit D4 is a logic 1. Okay, now bit D5 has no importance over here, so it's just a don't care, so as you can as is indicated over here by the cross symbol. And then we have, well, this particular instruction, this sim, okay, it also, well, enables serial data transfer. Okay, so it has got, well, the bit D6 and D7 bits of the accumulator data byte for this particular operation. So if we need to enable any serial data transfer, then we need to keep the bit D6 at a logic 1 voltage level. Okay, and if we just keep it to 0, then this particular feature would be just disabled. And the bit D7 would actually is basically known as the serial output data. So this particular bit present at the D7th position would just be set would just send to the serial output line, okay, or the serial output port whenever we have the bit D6 set to a logic 1 level. So this is how the sim instruction would basically function. Now let's just take up an example in order to, well, explain it a little better, in a little better way. So let's say we would just enable, okay, we would just enable the RST 5.5 line, okay, and disable the rest. Alright, so we need to disable the rest and keep the RST 5.5 line enabled only. So in order to do that, we need to set a particular code in the accumulator and then execute the same instruction. So what do? We need to, well, chart it out first. So first of all, we're not going to need the serial data transfer feature, so we just keep the D7 and D6 bits to logic 0. So first of all, I'm just gonna make out, or rather just chart it out over here. So this is D7, 6, 5, 4, 3, 2, 1 and 0 bits respectively of the accumulator data. So we just put here, let's say for D7 and D6 we just keep it to 0. Now D5 is an ignore or just a don't care bit, so we just keep it to 0 as well. And then we need to the bit D4 is basically reset, okay, if the flip-flop of the RST 7.5 line needs to be reset, okay. And our problem, well, it just says that we just need to enable the RST 5.5 line. So it doesn't matter whether the D4 bit is a logic 1 or logic 0. So for simplicity's sake, we just keep it to logic 0 so that the RST 7.5 line, well, it just remains disabled because of the input flip-flop. So we just keep it a 0 bit at the bit D4. Okay. Now D3 MSC mask set enable. Now we don't need to mask any of the bits. Okay. So we just what do? We just, well, need to enable the RST 5.5 interrupt line actually and mask the rest. So in order to enable the masking feature, we need to keep the MSE bit, that's bit D3, to the logic 1 level so that we can, well, mask the rest of the interrupt lines individually starting from the bits D0 to D2. So we just keep the bit D3 here at a logic 1 level. Okay, and now we can see that we need to, well, disable or mask the bits or rather the interrupt lines 7.5 and 6.5. so we just put D2 and D1 bits at logic 1, and since we don't need to keep, since we need to enable the 5.5 line, so we just keep the bit D0 at a logic 0 level. Okay, so now you can see we have, well, starting from the left, okay, we have 4 zeros as a group, okay, of 4 bits, and then starting from D3 to D0 we have another 4-bit group. So this just comes down to the hexadecimal equivalent of the code 0EH. Okay, so this is exactly the data byte that we need to load into the accumulator in order to get this job done. So we write here the program code, well, MVI A, 0EH. Okay, now we have just loaded this code into the accumulator, and now just we declare the instruction sim. Okay, so this, what it just does is that it basically enables the RST 5.5 interrupt line, okay, and it just disables the rest of them. Okay, so this was one example of how to use the sim instruction to control the interrupt lines, the RST interrupt lines, basically. Okay. Now, next up, we got the RIM instruction. Okay, now the RIM instruction actually stands for read interrupt mask. Now, let's say you've written, basically, you've written a very complex programs and which involves, a lot of interrupt instructions and all. And now the programmer, let's say, has forgotten which of the interrupt requests or which of the interrupts are basically enabled or disabled, or which of the interrupt requests are pending right now. He needs to, design a system to monitor and all. So, what could he do? Now, the 8085 under such a situation provides a getaway with the RIM instruction. You see, whenever you have a lot of interrupts are coming in, well, few of them have been, a few of the interrupt requests have been, well, completed, okay, or the rest have been, a lot more is pending and all. Now you don't know, or you need to get the status of what the interrupt system is currently at the present moment. Okay, so all those status and even what type of input bit you're getting through the serial port, okay, or through the serial input port, all these information, okay, basically is obtained or retrieved if we use the RIM instructions. Okay, now what we do is that if we just go straight forward and declare or just write in the program, RIM, then what it basically does is that after executing the RIM instruction, what happens is that the accumulator, so this is basically the accumulator content. So I'm just going to write that down over here. The content of the register A. Okay, so whenever you just write the instruction RIM in any part of your programming code, okay, the accumulator is loaded with an 8-bit data, or just a data byte, you can say that, whose each particular bit has a meaning, okay, has a special meaning over here, and these could just be understood if this particular diagram is kept in mind or remembered. Okay, so as it says, now let's say the accumulator is loaded with a particular data byte, okay, starting from, let's say, D0 through to D7. So we see over here that if the bits D2 to D0, any of them are kept at logic 1, then it means that the corresponding interrupt line has been masked. Okay, so that's what it just means over here. So interrupt masks if the bit equal to 1, which means that if we'd had, let's say, the D1 bit at a logic 1 level and the D2 and the D0 bits are at logic 0 level, so this means that the RST 6.5 line had been masked. Okay, so this is what you should understand if you just keep this diagram in your mind. So it just gives you the status of your interrupt system. Next, the bit D3 stands for IE, which means interrupt enable. So it just gives you the status of whether the interrupt enable flip-flop is set or reset. So if this bit, that's bit D3, is at a logic 1 level, then you shall understand that the interrupt enable flip-flop has been set. Okay, and if it's a 0, then it's obviously a reset. Okay, that's could be understood. Next, we have the bits D6 to D4, where these particular bits, that's D6 to D4, they monitor for pending interrupt requests. So if any of these bits starting from D6 to D4, if any of these bits are at logic 1 level, then it means that the corresponding, the particular interrupt request on the corresponding interrupt line is pending at the present moment. Okay, and finally we have the bit D7 that monitors for serial input data bit. Okay, so if we're having any kind of serial communication operation going on with the 8085 currently, then it also gives it the status of what bit we're taking as input through the serial input pin. Okay, so all these information could just be obtained by studying the data byte that is just loaded into the accumulator. So using the rim instruction, we can just obtain an accumulator data byte that gives you the status of your entire interrupting system, as well as also gives you the status of what sort of serial input data bit that you're basically receiving. So as an example, let's say if we would request for this kind of status using the rim instruction, and let's say if the accumulator data bit is 49H. Okay, now for the data byte of 49H loaded into the accumulator, if we just translate it into binary codes, okay, then we should get this something like this over here. Now for each of these bits, each of these corresponding bit levels that were just set to logic 1 and logic 0 levels, if we just study them, now we can get the following conclusions from here. So we can see that bit D0 sorry, set to logic 1 level, which means the RST 5.5 line interrupt line has been masked, and now the bit D2 and D1 being both set at logic 0 level, this means the 7.5 and 6.5 lines have been enabled. Okay, D3 equal to 1, which means interrupt enable flip-flop is set. Okay, and now we can see that D5 and D4 bits are logic 0, which means that the interrupt requests on the lines on the interrupt lines RST 6.5 and 5.5 have been completed, and only the RST 7.5 interrupt request is pending, since the bit D6 is equal to or has been set to logic 1 level. Okay, also we can see that the serial data input bit is a logic 0 at the current moment. Alright, so all this information could just be obtained from a data byte loaded into the accumulator if we use the rim instruction. Alright, lastly we got the restart instructions over here, which just form the category number 4. Okay, now each of the restart instructions, basically there are 8 restart instructions, starting from RST 0 okay through to RST 7. Alright, now these restart instructions from RST 0 through to RST 7, these are basically set by external hardware. So these instructions were basically let me just tell you over here before I just explain this point. You see, whenever we take any interrupt request via the INTR pin, okay, of the 8085 microprocessor. So if we're just taking any interrupt request via this particular INTR pin of the 8085 microprocessor, then we basically resort to using any one of these RST, that's the restart instructions. Okay, so RST here basically stands for restart. Okay, now depending upon which restart instruction we're just setting up using the external hardware, that determines what sort of hex code will be just transferred into the 8085 via its data bus. Okay, and whenever a particular RST instruction is taken up or acknowledged by the 8085 microprocessor, then the program control gets transferred to any one of the restart memory addresses, as you can see over here on page 00. Okay, depending upon which sort of depending upon the corresponding RST instruction that the 8085 has received. Let's say by the external hardware we just set the RST1 instruction. Okay, now for that, if there is an interrupt request on the INTR pin, we just send the RST1 interrupt request, okay, or restart instructions. So basically they're used in conjunction with interrupts, okay, through mainly via whenever we're taking the interrupts via the INTR pin of the 8085. So for the RST1 instruction, the corresponding hex code being CF, it just instructs the 8085 to direct the transfer of the program control to this particular memory address, that is 0008H. Okay, so the entire program control gets transferred to this particular memory address. Okay, similarly, if we would use the RST4 instruction over here, then the corresponding hex code would be E7, and the program control would transfer to 0020H memory location of the external RAM chip connected with the 8085. So these instructions are basically, you can also call them as a single byte call instructions, but they are equivalent to single byte call instructions. We just help transfer the program control to certain specific memory addresses. Okay, and all these memory addresses are referred to as the restart address. The program actually begins executing from these addresses. It just gets transferred to these locations, and all these locations is set according to the hex code that is received, which are designed using external hardware. Okay, so the detailed description about this kind of an interrupt based system is given in the interrupt tutorial, so kindly check that out for further details. Now, apart from that, we have certain other instructions, certain other interrupt instructions where we don't need any external hardware, okay, but yet they result in certain restart functions. Okay, so here for the interrupts received through the pins trap, RST 5.5, 6.5 and 7.5, we don't need any external hardware to set the memory restart addresses. Okay, but whenever any interrupt request is actually coming onto any of these particular pins, then the program control automatically gets directed to their corresponding restart addresses over here. So in a way they're also being executing a restart function to direct the program control to their specific memory restart locations. Okay, so this is just a brief account on the restart instructions over here, and with that we just come to the end of this tutorial video, where we just wound up the necessary things you need to know about the interrupt related instructions. So we're going to meet you in the next tutorial. So till then, keep watching and bye bye for now.